In this example, we're going to consider a building which is a semicircle. So it's going to look like that. And that building is at sea level. And there is going to be a wind coming from the side, like this. The cylinder will have a radius. So from this is the center of 0, then it's got a radius of r0, and this would be minus r0 in Cartesian coordinates. We have a wind speed coming from the side. We've got ourselves a rho infinity and a p infinity, which are known, so the ambient pressure and the density. We need to determine the lift force on this building, as the building is lifted a tiny bit from the ground. So you could evaluate the ground as this dashed line, and we see that the building is just off the ground, and we can apply potential flow theory. We're going to assume that the pressure that we're finding just underneath the building in that gap is going to be equal to the pressure that we're finding at the stagnation point, so at the point here and here. So that's going to be my stagnation pressure, PS. Right, and so now what we want to do is we want to evaluate what the pressure distribution along the surface of the building is, and then calculate what the lift is using potential flow theory. Okay, so that's going to be our aim. What is going to be the lift on this building? So we've got ourselves lift L prime, which is going to be the integral from minus r0 to r0 of the pressure on the lower side minus the pressure on the upper side, and we integrate that across x. So we've got x running in that direction. Okay, so we know from Bernoulli's equation that my pu on the upper side must be equal to p infinity plus a half rho infinity v infinity squared minus a half rho infinity v squared. And we know for a cylinder that v is actually minus 2v infinity sinus of theta. So that was derived in the lecture notes. PL is the stagnation pressure. It's equal to PS that I've defined here. And that stagnation pressure must be equal to P infinity plus a half rho infinity V infinity squared. Okay, so now what we can do is evaluate what PL minus PU is. So PL minus PU is equal to P infinity plus half rho infinity V infinity squared, that thing, minus, exactly the same terms, rho infinity V infinity squared, minus a half rho infinity V squared, like that. Okay, so we see that these terms are the same. So therefore my PL minus PU is going to be half rho infinity V squared, which is going to be equal to 2 rho infinity V infinity squared sinus squared theta. Okay, So that's good. So now I've got my PL minus PU in polar coordinates. So I would like to actually transform my integral from Cartesian to polar coordinates. In order to do that, I need to define a given theta. So I'll do that now. So we can define theta as this angle here. If we do that, then we're going to have theta 0 here, theta is equal to 0 here, and theta is equal to pi here. Okay, so if we define it like that, then we know that x is going to be r0, which is the radius of that cylinder, times the cosinus of theta. Right, from this it follows that dx can be defined. Dx is going to be dx d theta, isn't it? So we take the derivative of my x to theta. So if we do that, we're going to get the derivative of that cosinus, so we're going to get minus r0 sinus of theta d theta. So now we've got dx in polar coordinates and we've got PL minus PU in polar coordinates. So we can transform our integral for L prime. So the expression for L prime was the integral from minus R0, and minus R0 is equivalent, as we can see at the top here, to theta is equal to pi. So we've got now an integral from pi to R0. What's the equivalent to R0? That's this theta 0 here. So we're going from pi to 0. Good. Then we have PL minus PU. Well, we have an expression for that. That's 2 rho infinity, v infinity squared, sinus squared theta, d theta. Dx. And dx we've got an expression for, which is this one. Sinus theta d theta. There we go. So we can evaluate that integral. We're going to take all the constants outside the integral. So we've got a v infinity squared there. We've got ourselves a minus sign, actually. So it's a minus sign. We've got ourselves an r0. And then we've got that integral from pi to 0 of the sinus to the power of 3 d theta. So we need to evaluate what that integral is. Now one trick you can always do is you've got the bounds of this integral go from pi to 0. So if you swap the bounds, then you basically get rid of the minus sign. So that's something useful that you can always use. So that's 2 rho infinity v infinity squared r0. And then now I swap the bounds and I got rid of the minus sign all the way at the front of that equation. So that is the sinus to the power of 3 theta d theta. And that's a standard integral that we can evaluate. So this is going to be equal to 2 rho infinity v infinity squared r0. And then we substitute our standard integral, which is going to be minus sinus squared theta cosinus theta. We divide that by 3. Minus 2/3 of the cosinus of theta, and we evaluate this entire thing, evaluate it from 0 to pi. Right, so that's the integral we need to evaluate, and so what we get finally for L prime is going to be equal to all those constants that we had before, v infinity squared r0, and we've got 2/3 plus 2/3, which is 4/3, and 4/3 times 2 is 8/3 rho infinity v infinity squared r0. And that's going to be the force on that building. So the building will be lifting up. It's like a tent on a camp. If you leave the door open, it wants to go up. And this is a similar kind of problem. So that's this question.